Okay, hello everyone and welcome to my second tutorial on the exploit development process. This time I will talk to you about the basics of exploit development with an example of a direct buffer overflow. But first let's do a quick wrap up of our last video, which was called Basic Fuzzing with Sully. During our last video we visited the exploit database website to look for a nice test candidate, and we found the PCman FTP server. We downloaded and installed the application and started fuzzing. As a result, we ended up with a text file showing us use cases that led to a crash within this application. During this current session, we will have a closer look at what happens within the application while we crash it and how we can control this crash to make the application execute a payload we provide to, for example, open up a backdoor to the system. During this session we will spend quite some time in this program, which is the Immunity Debugger. To give you at least some basic knowledge about what this program is about, we have to do some theory about how a computer manages memory and how it keeps track of the program flow. Please keep in mind that this will really be the least knowledge you need to have to continue, and I would really recommend you to read some more tutorials and books about this stuff to get more background knowledge. You will find some links in the description to this video. Okay, so let's start with some theory using the Immunity Debugger. Here you see already in that window. A debugger can be attached, for example, to a process, and it will give us an overview of the current memory state, what is the content of the stack, and it will disassemble the operations that are executed. Let's start with the memory part. Let's start here on top. We have the EAX register. This register is also called the accumulator register, and it stores addresses to values used to perform simple calculations as additions or subtractions. Next we have ECX, which is the count register. Here values are stored, used to keep track during loops. Then we have the data register. This is the register which can be described as an extension of EAX. It's used for string operations and for more complex calculations like multiplication and division. Next we have the base register. This is a register, you could describe it as a general purpose register to just contain addresses to all kinds of values. Now let's have a look at the stack. The stack you could describe as a scratch pad for the computer. So here it could just add values it needs for later usage, and it can read values. What is important about the stack? A stack always has a base address, a bottom address, which is the EBP, and it always has a top address, which is the ESP, the stack pointer. During the execution of a program, the computer can create multiple stacks. So there's, I would say, is always more than one stack, and the computer always has to keep track for the current stack what's the lowest address, the base address, and what's the highest address, the stack address, pointer address. Now this can be a little confusing here. If you have a look at the memory addresses, the stack always starts at higher memory addresses, and the lingo is that you say it grows towards lower memory addresses. So if you have a look here, for example, the base pointer, which points at the bottom of the stack, is at a higher address than the stack pointer, which is the top of the stack. And one more pointer, we have here the instruction pointer. This pointer always points to the next operation that is about to be executed. So if we have a look here at the disassembled view, here we have the EIP address, so you see it's the same, and we know the next operation that is performed is a return, And also here we have an information pane, so we will get some more information. For example, here it shows it will return to this address, and we know what will happen next. To better understand the stack program execution and the registers, let's do one quick theoretical example. Here we have some pseudocode. We have a main function and we have a test function. Within our main function we have a variable named output where we store the string banana. We then call the test function where we have output, so banana as a parameter. We jump to the test function. The test function will take our banana, it will print the string banana and then return to our main function where we will then exit the program. Speaking of execution flow, we will start executing main, then we will jump to the test function and then we will jump back to the main. We will talk about two different stacks here. We will have a stack for the main function and we will have a stack for the test function. Let's have a look at the disassembled view. Let's imagine we start the program, we attach it to a debugger, and at some point our instruction pointer will land at this address. At this address it will execute the operation move the content of EBX into EDI. The meaning of this is now not relevant for us. The instruction pointer will then go to the next operation, which is here, which states push EAX. This means take the value of EAX and push it onto the stack. On the right side we already have our main stack. As you remember, the stack grows from higher addresses to lower addresses. Our base pointer points to the bottom of the stack and the stack pointer points to the top of the stack. Executing this function would mean we take the content of EAX and push it on top of the stack, so we have to execute ESP to point now to a lower address. Next we will execute this function, which is called test function. So let's have a look here. So this is where we will jump from the main execution to the test function. What is important for us is at one point the test function will be over and the program flow needs to jump back to continue in the main function. To remember the next address where we will continue the execution of the main function, we will take, or the computer will take, this memory address and will also push it to the stack, and this is the so-called return pointer. So this will be the next execution where we will return after executing the test function. So let's adjust ESP and we have the return pointer here. Next instruction that's executed is this one. It is in the test function because we called the test function. We will now jump here, and the first thing that happens here, and this is also called the prologue procedure, we will push EBP to the stack. So we will take the address that was here and push it onto the stack, and this is called the base pointer. Why do we need that? Once we return back here to the main function, we also have to restore the stack addresses. So we need to rebuild the stack as it was before. Next operation is move the content of ESP into EBP. So we will now take EBP here, and during the following operations, EBP will always point to the stack frame pointer. What happens next is a subtraction, so we subtract 0x40 from ESP, which means ESP will now point at lower addresses. Let's make it like this. Please remember, we grow to lower addresses, so a subtraction will calculate the next address, which is here at the lower address. If we do an addition, we will go to the higher addresses. Why is the computer now doing this? Within the test function, we take a parameter which is about to be printed. To reserve some space on the stack, we will now subtract this value of, what is it, 32, 64 bits, and this will be our buffer, and within this buffer we will have our string banana. And once this is done, EIP will return here, the stack will be restored. Let's have a look now what happens in the real program and the real debugger. So let us now start to develop our exploit for the PCMan FTP server. We start our vulnerable application at this IP address. We go to our attacker machine, and we already prepared the Python skeleton to perform a normal FTP connection. Quick explanation: we import the socket library, we create a TCP socket, we connect to our victim's IP on FTP port 21, we receive a welcome banner, we send the user anonymous, we receive an answer, we send the password test1234, we once again receive an answer, and then we quit the connection and we close the socket. Let's have a look if we can get a working connection. Python skeleton, we see user anonymous, password, and we quit. Perfect. Now let's take the results of our fuzzing session, and as we can see here, it seems like by sending an overly long password we will be able to crash the FTP server, and I will just pick this use case of the password right now for our test case. So let's adjust our Python script to crash the FTP server. Let's create some garbage consisting of like 5000 A's, and instead of the password we will now send our garbage, the A's, and let's see what happens. Python skeleton. Let's go here and we see the application already crashed. Let us now add a debugger to see what happens in the background. But before we do that, if you want to follow this example, you have to install the Immunity debugger, which you can find on this address, immunityinc.com products debugger. You have to provide just some basic information, then you will get a link to download the debugger. And please also go to github.com/Mona and download the Mona script. As a preparation, once you installed Immunity debugger, you go to the program files, Immunity Inc., Immunity debugger, or wherever you installed this application. You go to PyCommands and put the Mona Py in this folder. To verify if everything works correctly, you can start Immunity, go to this bar at the bottom and write !Mona, and once you get the usage information of Mona, you know that Mona is working. Okay, let's leave the debugger running. We have the crashed FTP. Let's open up the FTP server again and attach the debugger to the program. If for some reason you do not see the process of the FTP server here, start Immunity again and run it as an administrator. It should work then. So we attach the debugger. By default, the program flow will be paused, which allows us to get a basic overview before the program is running. And as you see, the program is really paused, so it won't react to any connection. To run the program, you can push this button to run, or you go to debug and run, and you see we don't have paused anymore, we are now running. You can also use the shortcut F9. Okay, so let us analyze now what will happen when we send this overly long password string. Let's send it again. And you see here we have an access violation when executing 41414141, which is also here the EIP, which means the program tries to execute something at this memory address. And you see here on the stack we have a bunch of A's. You see ESP points to the top of the stack, which is here, and it consists also of our A's, which for us is a good sign. That means that the garbage we send we have on the stack, and we overwrote EIP. Very quick, if you are not used to hex values, 41 is the hex representation of the ASCII character A. I would recommend in the beginning, let's see, do I have to take an ASCII table. Just use Google and look for ASCII hex table, and if you look here under hex 41, this is our representation of an A. Let's go back to some theory. What happened here and why is it good for us? In theory, we are back here at this design. Let's delete the buffer here. And let's assume the string we have here for printing is not banana, but it's 5000 A's. And the buffer we created here was just 64 bytes, but the 5000 A's we now put here is bigger than the buffer that was created. So let's put 4 A's here, let's put some more A's here, more, and so on, and so on. And at some point we will overwrite the stack that was here. So instead of the stack frame pointer, we have a bunch of A's. Next, we still have more A's, and instead of the return pointer, we also have A's. Instead of the content of EAX, we also have A's. And what we see happen is now, just imagine the test function continues, and it now tries to return to this address. But instead of this address, we have our bunch of A's. So EIP points to the A's and it tries to execute whatever is here. And whatever is here at 41, 41, 41, 41 is just garbage. The computer tries to read an instruction that is here at this address, but there is no usable address, so our program will crash. And let's just continue running it by Shift F7. And we get the error message. Don't know how to step command at address 41, 41, 41, 41. Try to change EIP or pass exception to the program. So here it will crash, it doesn't know how to continue, and it will end. The next step, what we will have to do is to figure out at which point in our garbage we overwrite EIP, because we want to get in control of this IPRESS. We want to put something useful in here. To do so, we can use Mona, but first let's configure Mona. We will use !Mona config -set working folder to C Mona %p. I will explain to you soon why we have to do this, and enter. Some basic navigation here. This is our log window. You will come to here by pressing the L. If you want to go back to the CPU view where we have our overview, just press C. Now we just set Mona's working folder to be Mona, and %p will be replaced by the current process name, in our case PCMan FTPD2. Now let's create a unique sequence with Mona by using pattern create of 5000. Mona will now create a sequence where we can, by providing like 4 characters, know exactly at which point of the sequence we are. So instead of the garbage, the 5000 A's, we will send this long sequence, and we will overwrite EIP. We will take the values of EIP, provide it to Mona again, and Mona can tell us exactly at which position we overwrite EIP. And we could just copy paste this sequence here, but we should take this warning of Mona quite serious. It says don't copy this pattern from the log window, it might be truncated, and it usually is. So we now go to our working folder, which we set to C, Mona, our process name. We have a pattern txt, and we will just copy this sequence from here. Let's put it instead of the ace. Oops. So instead of the ace, we now have our sequence. And let's just send it again. Here we close the debugger. The FTP server is also closed. We start it. And now we attach the debugger again. And don't forget to run the program. Now that our program is just it, let's see if that. Our garbage is the unique sequence number, and it will be sent as a password. Let's save and execute. So you see, we once again get an access violation, but now we are at a different point. So let's use Mona again, Mona. Now we use the command pattern offset, and we take the EIP address, which is 47326947. Pattern, and now this is once again the ASCII representation of our hex values, found in cyclic pattern at position 4926. Okay, let's test it. Oops. We delete the unique sequence. We now again use our ace times 4926 plus let's just take 4 B's and fill up the rest with some C's. C times we have 4926 and 4. Let's say let's just add 400 and see if it works. We restart FTP, attach the debugger, run, save our script, and send our skeleton again. And as you see here, we now have our 4 B's in here. Let's do it again to explain something additional. And also you see here on the stack the C's. So we first have our garbage, the ace. We overwrite EIP exactly here, and then this will be our potential later on payload we want to execute. Let's change something because I want to explain to you what little endian is. Let's put a C, D, E, F. We save again. So instead of the 4 B's, we have a C, D, E, F, with which we will overwrite EIP. I'll be a little faster now. It's running. It's saved. Let's send again. So as you see here, in memory, the computer stores values in the little endian format, which means it will reverse the order in which we provide our information. So here we have 43, 44, 45, 46, which is the representation of our C, D, E, F. This is later on important when you write, instead of just characters, you will put a memory address in here, that you have to write it here in the reverse order for it to make sense. Now that we have precise control over EIP, the next step is to figure out if we have a way to jump to the payload. In our case, the payload consists currently just out of C's, and later on we will replace the C's with our payload. How would we jump there? There are multiple ways. For example, you could replace EIP just with a memory address where you want to go to and then execute the payload. But the issue we have here is that the memory address starts with 2 zeros. 2 zeros are also called a null byte, and when you perform exploitation remotely, so using the network from one computer to the next, the null byte will just close the connection, and with a closed connection we can't perform any further exploitation. So it is necessary for us to avoid using a null byte. Also, I would say it's not really good practice to just jump to an address directly here, because depending on the program, how it was compiled and what kind of security mechanism it uses, this address might change up and restart of the system, and it is not reliable. What we might be able to use is, if you look at the registers here, ESP, the address of ESP, so the top of our stack, points to our payload, and also the ESI register points right in our payload. So let's use Mona now to see if we have this assembly instruction jump ESP or jump ESI somewhere within the program. We now use Mona modules -o first to just get an overview of the modules that come with the application. And as you see, this application comes with its executable and 2 DLLs that are used. The -o parameter makes sure we just see the application components. If we don't use the -o, it will take some time. We also see all operation system DLLs that are used. Very quick overview here. Mona shows us the modules that are used and which security is in place for these modules. Let's have a very quick overview. Rebase means that the base memory address of each module will be randomized, so it will be different up and restart. If it's true, it will be randomized. If it's false, this means this security is not in place. So here the base address will always be the same. Safe SEH, this will be in scope of our next video. SEH is a structured exception handler, which is like the error handling, the default error handling within Windows. We have ASLR, which stands for Address Space Layout Randomization, which will also make sure that the memory addresses used are always randomized and different. We have NXCompat, which is also called Data Execution Prevention, which means that a page in memory can either be written by the user but not executed, or it can be executed but not written to by the user. So if we could write our payload somewhere, this would prevent us from executing it, or we are not allowed to write something to a memory page, but we could execute it. And the last one is just to differentiate, is this an operation system, library, DLL, or does it belong to the program? And as you can see, the program modules are compiled in a way that are very insecure, and all of the libraries used from the operation system, in my case here Windows 7, is set to true. So as an exploit developer, we try to stick, for 2 reasons, to the components of the application. First reason is, thanks to the developer, the security mechanisms are not in place. And also, when we talk about reliability, it is always better practice to use the application components, because just imagine someone would use one of the OS applications Here in my case it's a Windows 7, I guess, Service Pack 1. And whenever you install a patch for Windows, or you install another service pack, whatever, it might lead to a patch of this DLL, and whatever address we might use from here, it might get changed. So the exploit is less reliable, because you need to write in your exploit later on, this exploit is for PCman FTPD version whatever, which hopefully still includes the vulnerable part, and Windows 7 Service Pack 1 with this patch status. Okay, so let's now first find our instruction at jump esp jump -resp in one of the modules that come with the PCman application. It will take some time. It will find some pointers, a total of 5, which are listed here. Jump esp or push esp red will have the same meaning. But once again, we have the issue here. We just have addresses with null bytes, which means we can't use these pointers. We can also have a look at jump esi, but still we are in the same modules. I expect to just see null bytes for esi. So here we still have the null bytes, so we can't use any of these pointers. We could now go to the Mona folder, have a look at the other pointers, because we have 106. But I can already tell you there will always be null bytes, so we can't use any of the addresses here. What we will now do is we will do some bad practice, but still to teach you the basics of the concepts. It should be sufficient. I will just pick one module that comes here with the operation system. Let's take what's easy. Let's pick a short one, NSI DLL -m NSI.dll. Oh, what did I write here? ESP-m. So it now loads some seconds, and here we have a memory address which points to the instruction jump esp. What we will do now is we copy this address, we will adjust our payload, so instead of CDEF we will now put in the memory address, and it's good practice to say from where you would take this address, OS, and here, to keep a better overview, we will just use a variable here, EIP, and for EIP we will use this address in reverse order, 73221477. Okay, let's save, go back, restart this. We have the PCman FTPD, we start the debugger, we attach, and what we will do first before we run the program, if you press Ctrl G, we tell the debugger we want to jump to the memory address, and here you see this is our jump ESP, we are still at the same address. We now press F2 to set a soft breakpoint, so whenever the program execution hits this address, it will stop and wait for us to continue. Now you might ask yourself, okay, why is this address still the same? ASLR was activated for this module here. It's a true for ASLR. ASLR will just randomize the address up and restart of the whole operation system. So if we just crash the application, we are fine. The memory addresses will always be the same, but once we restart the whole computer, the memory address will be different. Okay, let's now run the program, go back to our CPU view, we saved it, and let's send our coin script. So as you see here, breakpoint at NSI and the memory address, we hit the breakpoint, we jump to ESP. What you now have to do is, or what we want to do is, instead of just push this button again, run, we want to step into. So we push as F7, which means just do one instruction, and then have a look, jump ESP. And as you can see now, we are at this memory address, which was the top of the stack, and we have our C's here. Now that we found a way to jump to our payload, which right now consists just of C's, we need to find so-called bad characters. Bad characters are characters that we are not allowed to use when we create our payload. As we've seen before, a null byte is something we can't use when we do remote execution. So we can already define a null byte as a bad character. But what other bad characters might we have that we are not allowed to use? Once again, there's a Mona module that will help us. We will use Mona byte array to create a list of all possible hex values, and we will also define a bad character we know already, which is the null byte. So as you see here, Mona will create an array including all hex values except the null byte 00. We will now copy this for our payload, and what will happen next is we will send all the hex bytes as a payload and will then compare this creation, which Mona also stores in bytearray.bin, with what is found in memory, and if there are any differences, we know that there is a bad character that causes the payload here to change. So let's add a payload equals. So we have the payload here. Instead of the C's, we will now take the payload and we just fill it up with some knobs. A knob which has the hex value of x90 is just a no operation. So it will just tell the CPU, do nothing, go to the next instruction. Let's just add, I don't know, 100. Okay, let's restart the program. Attach to the right process. Let's jump again to the right address. One hint, sometimes when you use Ctrl-G to jump to an address, it will jump to a wrong address. I don't know the reason. Just do this again and then you will end up at the right location. F2 again, set the breakpoint, F9 to run the program. Now we send the skeleton with a new payload. We hit the breakpoint and we see this is where we expect our payload. And already after 09 we see that 0A is missing and something is messed up. But let's use Mona to compare. Mona compare. Now we have to provide the file where the original byte array is stored. Mona pcmanfd pd2/bytearray.bin -a, and here we have to provide the correct address where the payload starts. In our case it's 0012ed6c. Unable to find file, byte, okay, I forgot T once again. Mona will now compare the byte array file with what is found in memory, and as we see here, at 0A we have a mismatch. So we already know that 0a is also a bad character. Now we have to repeat the step we already did. We create a new byte array, but now we also add 0a as a bad character. Let's have a look really quick in our ASCII table what 0a stands for. 0a is a new line feed, which makes sense. This is like sending a carriage return. And if we come back to what we are actually doing, is we are sending a username, we are sending a password, and this is also a carriage return new line feed. And having this here in our payload means that we send the payload until here, and here we would push enter, so return, and whatever comes here following would not be sent as the password anymore. It would just be something else. So that would be not good for our payload. That would break our payload. What you can now do to save a step is, if you look further, 0d is also carriage return, so we can expect that we are not allowed to use a 0d also. So let's save a step. We will also define right away 0x0d as a bad character. Oops. Mona byte array slash 0a. Okay, now it works. If you set the parameters correctly, it won't give you error messages. Let's take the new byte array. So as you see, 0a is missing, and we also took out 0d. Copy, paste. Zero A is missing 0d. Let's save and let's restart everything. pcmin, debugger, attach, Control G. Let's set a breakpoint, run the FTP server, send our current exploit again. We hit the breakpoint, and now as you can see, our payload starts here and we go down until the very last one, F, which is here. But let's nevertheless use Mona again to see if we don't miss anything. Byte array dot bin minus a, the address where our payload starts, which is still 0012ed6c. And it says unmodified. Hooray, normal shellcode unmodified. Now that we are aware of our bad characters, we can create our payload and make sure that we don't include these bad characters in the payload code. I will now use Kali and the tool msfvenom that comes with the Metasploit framework to create a payload. We will have the parameter -a for the architecture, -- platform for Windows, -p to define what kind of payload we want to have. In this case, I will use a regular bind shell TCP. -b, we will define the bad characters that should not be within the payload, and with -f Python we define what the output format should look like. Now msfvenom will create the payload for us. We are now aware that the encoder Shikata Ganai was used to encode, and we have a payload size of 355 bytes. Let's now copy this to our script. So our payload will now be the buffer. We have buff But we cannot just add this buff, because if you look here, back on the stack, let's jump into ESP, just one step. Oops. You will see that we jump here to this address, but our payload already begins one address earlier. So if we would just add the payload right away, we would lose the first 4 characters, which would already render our payload unusable. To circumvent this, we will just pad this space with some knobs, which are the 0x90s times, let's be generous, we add 20. And by doing so, I can later on explain to you also what a so-called knob sled is. Let's save this, start again, file attach. We once again set the breakpoint. We run the program and we send our exploit. We once again hit the breakpoint. With F7 we just step into it, and as you see, here are our 20 knobs. We land just somewhere in the knobs, and we will slide down these no operations until we have our payload here that starts with DAC3. If we compare DAC3, this will be our payload. But if we try to step into it, you will realize that it fails. We have an access violation when executing. Why is this the case? If you remember, we used an operation system module for our jump ESP, and Mona, let's have a look at this module again. -m, it was NSIDLL. You see here we have all the security mechanisms in place for NSIDLL, also the NXCompat. And NXCompat says if we write somewhere, we are not allowed to execute it. And this is why we get an access violation when we now try to execute what we have written. There are ways around this, but this is not basic stuff. This is more advanced. We would need to use return-oriented programming to first deactivate this security mechanism. In our case, we will cheat. We go to Computer Properties, Advanced System Settings, Performance Settings, Data Execution Prevention, and we will add our PCMan FTPD2 to our exclusion list. Apply awk. So let's try it again. It might be necessary for us to restart the computer, but maybe it will also work right away. So once again, we set a breakpoint, we run it. Just remember, if you have to restart your computer, this address won't be valid anymore due to the ASLR. You would once again need to use Mona, jump, -r, ESP, search for module and take the new address here. So let's try sending our payload again now. Oops. We hit the breakpoint again. With F7 we will step into, and see now we will go along our knobs, and I will now just run the program again, and you see it's still running, it does not crash. Let's go to Kali now and try to connect there. 20 on port. By default the bind shell goes on port 4444, and we are on our target system. The program itself is still running. It won't accept any new connection, but it is not crashed because we just redirected the program flow to execute our payload, the bind shell. Just if we stop the bind shell and the program tries to go back to its normal execution flow, the program will then be terminated and it's crashed. So now we are at the end of this tutorial. I hope you enjoyed it. If you have any feedback or questions, feel free to use the comment section. I would also be very happy if you subscribe to my channel. I hopefully manage to get the next video up next weekend, where I will tell you something about structured exception handler overflows. Okay, so long, bye bye.